So good morning. I'm Emmanuel and in charge of business development for GreenWaves, and I'm gonna present GAP processors which have been designed for enabling AI at the very edge. So who are we? Who is GreenWaves? We are a fabless IC vendor and selling highly efficient RISC-V parallel processors for AI at the very edge, which means ultra low power. We have, of course, IC, but we're also designing, besides processors, dev kits, boards, and SDKs, and a lot of application software, which I'll present. We have offices. We started in 2014, and our first product is now in volume production, GAP 8. And we have offices in Grenoble, which is the head office, but also Bologna, Shanghai, Seoul, and Boston. So what is AI at the very edge? Well, it's about analysis of sensor data. So, so first you capture sensor data, so human, of course, the 6 sensors, but also beyond human, vibration, radar, infrared, ultrasound. And then when you do cloud processing, you send all of this. I cannot point here, it doesn't work, but you send all of this to the cloud through high data rate wireless. But of course on AIoT, and when power is critical, you want to interpret and analyze the data on the device, on the end device, and only transmit very limited amount of data through LPE1, for example, LoRa, Bluetooth, or NB-IoT. And that's what we do. So what machine learning is becoming an attribute of all IoT devices and here are a few examples of what GAP technology is enabling is workspace management with people counting object detection, also machine health monitoring, vibration analysis, people detection when people are falling, for example. Face ID, of course, that's a well-known, very successful application. Detecting sounds and analyzing them, text recognition for vision impaired people, biosignal analysis, of course, all the wearables, face detection, keyword detection, and gesture control. Let me show you. Okay, so what is GAP? So GAP is our product line of processors. GAP 8 is the first one. It's basically based on a hierarchical architecture based on a low power SoC MCU with its own controller peripherals, and then an embedded compute cluster. So basically, most of the processing you do, the always on, you do on the MCU part, and when there is an event of interest, you're going to fire up the compute cluster to do your AI or machine vision or signal processing. So agility is also key. We have many clock and power domain so that we only use what is required, and we can adjust voltage and frequency based on the compute requirement. And also we can go from one state to the other, deep sleep, a low power and a high efficient, high compute state very efficient, very quickly. On the programmability, well, it's all RISC-V based, as I'll show you in a second, and therefore it's fully programmable. And we're not dedicated to CNN. We can implement other type of networks, not only fully connected, but also the other families, and also signal processing. And we can switch from one model to the other one dynamically. So it's GAP 8. It's the first generation that's now in full production with a few customers. You can see some of these demos on our booth. Our first processor is in TSMC 55 nanometer. It's got, so as you can see here, It's got the MCU part with the RISC-V, that's called the fabric controller, and also its peripherals. So that's the first RISC-V. And then the compute cluster, which you start when you need to run heavy-duty algorithms. It's based on 8 RISC-V with a hardware accelerator for convolutional and its own memory. Now, it's now production qualified, as I said, and shipping in volume on customer products. So 2 examples we're demoing here on our booth are the Face ID. So we develop also software, a lot of software. By the way, we are compliant. Well, as RISC-V is open source, all our software is also open source. So that's all available on the GitHub repositories. And the 2 examples that we develop with a full reference platform, so customers can take all of this, not only the chip, but also the schematics and all the software, and take it from there. So we have 2 fully developed use cases. One is Face ID, and you can see how the analysis phase is the face detection. That takes only 1 milliwatt. And then when you detect a face, you do the face re-identification against a database. That takes 22 milliwatt and 400 milliseconds. So that's when you switch from here. Face detection is done on the MCU part, and re-identification on the compute cluster. Then the second one, which we announced yesterday, is the infrared people detection for occupancy management. So we also build a reference system, which we have here, that's based on a LINRED 80 by 80 infrared sensor. And here we're doing image processing in the background, and then human detection. And that takes only 4.4 milliwatt per frame per second in 22 microseconds. We've achieved an accuracy of 99%, and which gives you about a more than 5-year battery life on a single battery. And that's the full system we have here. You can see the animation here when people are moving on a room. So they're sitting around a table here, or moving here. Okay? So that's when privacy is paramount, and you don't want to disclose who is there. So infrared is actually commonly used for this building management application. So this is the application reference platform we are releasing. So it's a full board based on our GAP mod. GAP mod is a module with just the processor and the memories. And we've used that to build this reference platform with the Thermi sensor from LINRED, and it includes a BLE module. So we here connect to a smartphone. And that's a fully available schematics and layout. And that's called GAPOG-B reference board. And it comes not only with the schematics, but also with the people detection neural network and the training data set we've used. And then the application software on the Android phone. This is a power analysis of the full reference platform you just saw. Well, depending on how many images per second you want to acquire. So if you acquire 1 per minute, then the battery like this, such a battery is going to last 1.5 years, 1.8 years. But if you acquire only 6 per hour, then 1 every 10 minutes, they're going to last 12 years. Our offer also includes what we call GAP SDK. So SDK is a set of tools. It's GCC based as the RISC-V is, and we have a number of API for drivers and RTOS supported. So we have quite a few of the open source Zephyr, FreeRTOS, PulpOS, AliOS, and then the core of this tool is actually what we call JVSOC, and that's a cycle-accurate SoC simulator software, but actually runs 20 MIPS in software, so you can run, real time some application, and it's very precise, between 5 to 10%, and it comes with nice diagram viewfinders. At a higher level, we have what's called gap flow. Gap flow is a high-level tool set that takes basically graphs of neural networks, for example, coming from PyTorch or TF-Lite, and will convert them basically into gap code through a number of tools. One is the NN tool, which is neural network tool for the graph conversion, and that includes training quantization. And then the autotiler will actually split the memory into the constraint of the gap 8. So it will manage for you automatically how memory will flow from L3 into, which is outside of the chip, into the main L2 memory inside the core, the gap 8, and to the local L1 for each core. And that's all handled by this tool. You don't have to do that manually. Okay, here's an example of a benchmark, two benchmarks actually, CFAR10, and which is a simple image processing, image recognition, and then a more extensive MobileNet V1, compared to an ARM, a Cortex M7, which is the STM32H7 dual issue ARM. So we basically, okay, there is a process difference here. We are in 55 nanometer gap 8, and the M7 is in 40 nanometer. And we have taken basically the same frame rate, okay, to make an apple-to-apple comparison. So we actually only needed to run at 150 megahertz instead of 400 megahertz on the M7, and you can see that we achieve a 16x or 15x, depending on the algorithm, a lower power with for the exact same frame rate. Okay, so that's you're more than an order of magnitude lower power with a gap 8 compared to a Cortex M7. Now, the new product that we announced in December at RISC-V Summit, and that's going to be in production next year, is gap 9, as you could have guessed. And what it is, it's pretty much the same architecture, but in a leading low power process, because we went with Global Foundries 22 nanometer FDX, so FDSOI. And on top of that, we also tuned and basically added a lot of new functionalities, such as floating point and matrix compression on the fly, and a lot of security new features as well on gap 9. So all in all, we're able to get a 10x larger, more complex problems on gap 9 than gap 8 for 5 times less power. So that's very significant, but we made sure we kept the same agility and programmability, or actually increased it even further on gap 9. So to recap, we not only sell the chips and the SDK, but also a number of boards. This is, so gap 9 boards are going to be available in 2020 for lead customers. Gap 9 simulators has been used by lead customers since May 2019, and we have refined the architecture of Gap 9 with some of these key customers. Gap 8 is in shipping in production, and all these, the occupancy management firmware is now available, and we have a number of other Gap Arc boards for Face ID, for example, and also for sound pickup. So please come and visit our booth right there to see these demos and ask any questions you may have. Any questions? Thank you.